Hello everyone, this is the first video clip of week 15, and I'd like to continue to talk about this Moore circle thing in chapter 14. So last time in the previous the video, I introduced the two equations, one for sigma x prime and the other one tau x prime y prime. So we started from the state of stress in the plane stress condition, and plane stress condition means all the stresses along the z-axis is going to be zero, and I gave you the two examples of those. One would be the kind of a plate, and then we apply the forces only in the in-plane direction so that there's no stress in the out of plane direction. So that could be one of the examples. The other one, the circular shaft on the surface, we can say that it's going to be the plane stress condition. When it is considered as a plane stress condition, we can simplify the cubic into this two-dimensional plane. So this is going to be sigma x, it's going to be sigma y, and by the way, I'm drawing all stresses in a positive direction right now. So this is going to be tau xy, tau xy, tau yx will be equal to each other. So we can express any state of stress with these three stresses, sigma x, sigma y, and tau xy. And somehow when we have a change in angle, then I went through the derivation. So we finally got these two equations, sigma x prime and tau x prime y prime. And you can easily find out the sigma y prime, because sigma y prime, when you put the angle, so whatever theta plus 90-degree phase difference, then you can have experience the expression of the sigma y prime. So anyway, the sigma x prime was sigma x plus sigma y over 2. And then here we have sigma x minus sigma y over 2 times sine of 2 theta plus, oh no, this is cosine, sorry. So here is the cosine 2 theta, and then tau xy with sine 2 theta. And then tau x prime y prime is equal to negative sigma x minus sigma y over 2 times sine 2 theta plus tau xy of cosine 2 theta. So we derive these two equations from this wedge, right, with all the stresses using the equilibrium equations. And also I said that when we take this term to the left-hand side and then square for both sides for the equation number 1, and do the same thing for the second equation. So we square this left-hand side and square the right-hand side, combine these two together and simplify it. We finally get the expression like this, sigma x prime minus this, which is sigma average. So sigma average squared plus tau x prime y prime squared will be equal to something squared. I'm going to say r squared, where r is equal to square root of these sigma x minus sigma y over 2 squared plus tau xy squared. So we can express this equation in a circular, the equation of circle, right? Okay, so here I'm going to draw a circle, and that circle is called the Moore circle. And one of the things that I mentioned that when you develop the Moore circle, there are two different ways, but according to the Hibbeler's textbook, and I'd like to be consistent with this, the formulations and the sign convention and everything, he determined that x-axis, which is the axis for the normal stress, sigma, and the y, the vertical axis, this is for tau, the shear stress. The positive direction of tau, it goes downward. Okay, so that's one thing that we have to make sure and you have to keep in mind that this tau goes down. Anyway, so I'm going to talk kind of repeat and review the development of Mohr circle. To develop the Mohr circle, we have to start with 3 points, C, A, and G, and these are the same letter in the points according to the textbook. The first point is going to be the center, and the coordinate of the center is going to be sigma average, and the vertical component is going to be 0. So the center is always on this x-axis because, because of this formulation. The second point in the coordinate of the second point A is going to be sigma x, comma, tau xy. The third one is going to be G, sigma y, comma, negative tau xy. So typically we have these 3 stresses, sigma x, tau xy, and sigma y. When we have these 3 stresses available, then we can easily identify these coordinates, right? Sigma average is sigma x plus sigma y divided by 2, and then sigma x is sigma x whatever, given sigma y as well, and tau xy. Okay, so when you calculate the sigma average, just find out that value here. For example, let's say sigma average is located here. Then this is going to be point C. I'm going to use a different color. This is point C. And let's say we have all positive number for sigma x, sigma y, tau xy, just as an example. And sigma x is here. And then tau xy here. So that we can easily find out the intersection point. This is going to be sigma x, comma, tau xy. By the way, again, I just assumed tau xy in a positive value, and based on this sign convention, the positive direction goes downward. So this is going to be the point, and it is based on sigma x and tau xy. So this is point A. Okay, and we can do the same thing for point G. And by the way, the length between this point C and point A, straight line, this is going to be the radius of this circle. So I'm going to talk about it in a minute. So sigma y, because sigma average is the average value between sigma x and sigma y. So this is sigma y. And then negative tau xy. So let's say this is tau, negative tau xy. We can think about the point here. And it is always opposite direction of this point A to C, okay? So you can always see that there's this point G and point A, and also point C, the center of the circle will be on the one straight line. So when we identify these 3 points based on the given information, sigma x, sigma y, and tau xy, we can find out these 3 points, right? And then we're going to construct a circle based on this. So I said the length between C and A will be the radius, right? So keep that radius and then draw a circle. Sorry about my poor drawing. Looks like the circle, right? Okay. So this is going to be Mohr circle. And this Mohr circle, based on these 3 points initially, will tell us a lot of different things. So first of all, sigma average, that's the average normal stress. And then any points on this circle will represent the state of stress. So for example, these 2 points, top and the bottom, I can easily say that this point, the y coordinate, the coordinate on the vertical axis, will be the maximum value here, right? So that is going to be tau max. And I'm talking about the in-plane direction of the shear stress. And with similar reason, this value is going to be negative quantity of tau max. And the points in your textbook, this is point E, and this is point F. So the coordinate of point E is going to be, X coordinate is going to be the same as the center, which is sigma average. The Y coordinate is going to be tau max. And what is tau max, by the way? This is exactly same as what? R, the radius, distance from C to E directly. So this tau max will be equal to R. And similarly, we can say at point F, the coordinate is going to be sigma average, comma negative R or negative tau max. Okay, so those are two special points on this Mohr circle. There are other two special points, which is this one, this one. So two intersection point meeting with this horizontal axis. This one is called the sigma, the point, point B, and the other one is point D. And B and D, you can see that I said any point on the circle will represent the state of stress, and this is the point we can maximize the normal stress. Normal stress is the quantity along with this horizontal axis. So we can see that the minimum value start from here, and then we can maximize the sigma value along this line at B, and then it's going to be average value and going back to minimum. So this corresponding sigma here at point B is called the sigma 1, okay? And the vertical, the y coordinate is going to be 0. And the corresponding normal stress at point D is called sigma 2, and the y coordinate is going to be 0. So sigma 1, sigma 2, those two special maximum and minimum normal stresses are called principal stresses. I mentioned it before in the previous the previous video. So sigma 1, sigma 2 are called principal stresses, and sigma 1 is the maximum. Sigma max, sigma 2 is a sigma min, okay? And the angle from this current position to the principal stress is called the third theta p, and the angle from here to here is going to be 2 times theta p. So actually, in general, whenever you change the angle in the real space, you have to double the amount of that angle in this Mohr circle thing. So we're going to talk about it in the example problem later on. So this is how we can construct the Mohr circle, and I'm going to go over the example problems and how we can use this Mohr circle to solve the problem. Okay, so the example problem that I'm going to work on is I'm going to go over 2 example problems. Example 14.8 first, and then we're going to go over 14.9. Okay, so I'm going to save it and then clear. Okay, here is example 14.8. So the question is this. Here we have a state of plane stress, and it looks something like this. So this is a stress block, represent our current state of stress. So here we have 20 megapascal is a compressive stress, and 90 megapascal going this way. So it is going to be tensile stress. And then for shear stress, we have 60 megapascal. So going this way. Okay, so this is the current state of stress. And then the question is, determine the maximum in-plane shear stress at this point. So the question is, determine the maximum in-plane shear stress, which means tau max. Okay. If you want, you can have a formula for tau max and then just substitute all the numbers based on these the cubic. But I'm going to solve this problem using the Mohr circle. So to develop the Mohr circle again, we have to start with how many points? 3 points, C, A, and G. Okay, so let's think about the coordinates of those 3 points. To do that, we have to identify this sigma x, sigma y, and tau xy first. So sigma x, sigma y, and tau xy based on these given state of stress. So sigma x, that is the normal stress along the horizontal direction, which is 20 megapascal in magnitude, but it is a compressive stress. So I would say the sigma max is going to be negative 20 megapascal. Sigma y, that's the stress along the vertical axis, and we have 90 megapascal. It is a tensile stress. It's going to be positive 90 megapascal. To have the right direction, the right sign, the positive, negative thing, especially tau xy, this is very important because when you miss that sign, you will have a totally different answer. Okay, based on the sign convention of this stress block, all these tensile stresses for both sigma x and sigma y that will have a positive direction, positive sign. For tau xy, this is a positive the sign. Positive shear stress is kind of a pair, okay? So tau xy is going to be 60 megapascal. So we're going to start from here. So when we identified sigma x, sigma y, and tau xy with the proper signs, then we can define the coordinates of these 3 points. The C. So the first point is the center. The C, A, and G. C, the x coordinate is going to be sigma average. Sigma average means sigma x plus sigma y over 2. So negative 20 plus 90, which is 70, divided by 2 is going to be 35 in megapascal. So the unit is megapascal here. And y coordinate for C, the center of the circle, Mohr circle, is always equal to 0. Right. Now, at the coordinate for point A, sigma x comma tau xy, the sigma x is negative 20, tau xy is positive 60. G, sigma y comma negative tau xy, so sigma y is positive 90, and negative tau xy is going to be negative 60. So these are the components of these 3 points. So I'm going to construct the Mohr circle. Again, this vertical axis, we have to draw a positive direction going down, and then 35 and negative 20, positive 90, and positive 60 and 90. Okay, so this is going to be my horizontal axis. This is for sigma, this is for tau, right? Okay, so for the center of the circle is here. So here we have 10, 20, 30, 40. So this is going to be 35. This is 35 megapascal comma 0. This is point C. Point A is negative 20, so we have to go the other way. Negative 10, negative 20. So this is going to be negative 20 here. And then positive 60. So this way. 1, 2, 3, 4, 5, 6. So negative 20 with positive 60 here. This is negative 20. This was positive 35. So this is going to be point A. Okay, now we have 90 and negative 60. So 1, 2, 3, 4, 5, 60, 70, 80, 90 here. And then negative 60. So 1, 2, 3, 4, 5, 6. So let me do my best. Here we come. This is going to be my point G. So I'm going to use a different color. So again, I said these 3 points should be on the same line. if you use a exact proportional relationship, it's kind of on the same line, right? Okay, so this is going to be, the length of this is going to be r. You can easily find out the r from the equation, or using the Pythagorean theorem, the base of the triangle is 20 plus 35, so 55. And the height of this the triangle is going to be 60, so you can easily find out that r as square root of 55 square plus 60 square. Okay, when you calculate it, I got 81.4. Anyway, actually, when you calculate the radius using these this triangle 81.4, if you understood the Mohr circle and the maximum in-plane shear stress tau max was equal to actually the magnitude of the r, the radius r, right? So the answer should be 81.4 megapascal. But I just want to keep going to draw and complete this Mohr circle and then show how we can identify this 81.4 megapascal from the Mohr circle. Okay, so these are the 3 points that we started with, and then we're gonna draw a circle from these 3 points. Here we go. I know this is kind of a bad drawing, right? All right, so let me try it. Do it again. So here, is it better? Anyway, so this is the Mohr circle based on the given state of stress. The maximum in-plane shear stress, that is the point where we can maximize the coordinate in the vertical direction. So either this points or this points in terms of the magnitude. And those were point E and F. E was here, F was here, right? In both cases, the x coordinate is going to be sigma average, comma, either positive or negative tau max. Okay, and that is exactly same as the radius, which is this length as well. So you can easily find out the r from here, or you can directly use this equation, sigma x minus sigma y over 2 squared plus tau xy squared. You'll get the same answer, 81.4. So that's how we can calculate the maximum in-plane shear stress. And the question is not asking the angle associated with the maximum in-plane shear stress, but when you estimate this angle in the Mohr circle I said is going to be twice the whatever actual angle in the real plane, right? So this angle is going to be equal to 2 times theta s. So theta s is the angle from this current condition. I changed the angle in the clockwise direction, the counterclockwise direction. So we have to go with the counterclockwise direction as well with this much. Theta s in the real space in the Mohr circle is going to be twice of the theta s. So in other words, when you estimate this angle, you can easily estimate this angle as this. Can you estimate this angle? Yeah, because we know this from this triangle, the base is 55, the height is 60. So from the sine, right, of this angle, let's say this angle is x, then not sine, this is sine, right? So sine of angle x is gonna be 60 divided by 55. So you can use the arcsine function. You can easily find this one, and then 2 times theta s will be equal to 90, which is this, minus whatever x from this calculation, then you will get, and then divided by 2, that is going to be theta s. Or you can use the tangent function as well. Am I right? Oh, I use a tangent, sorry. This should be tangent. Here we go. Okay, so that's how we can identify this angle. I'm going to save it again. So when you calculate the angle theta s, by the way, is equal to 21.3 in degree in a counterclockwise direction. Okay, so that is example 14.8. Let me go over the 14.9. So these two problems, 14.8 and 14.9, is very typical problems using the Mohr circle. Okay, so example 14.9. So the question is this. Again, here we have a state of stress is given. So we have 8 KSI. So here we have now US unit. And then 12 KSI in the vertical direction. 12 KSI. And then the shear stress going away. So this way, it's going to be negative. And the magnitude is 6 KSI. Okay, so this is the state of stress. A state of plane stress at a point is shown in this figure. Represent this state of stress on an element oriented 30-degree counterclockwise from the position shown. So what we'd like to know is, so this is the current state of stress, right? And we'd like to change the angle counterclockwise direction with 30 degree. So let's say this is going to be 30 degree. Then what we're going to do, I'd like to change the angle from the original state of stress to this, and then this angle is going to be 30 degree. Okay, then the question is, what are these normal stresses and shear stresses on the stress block when we change the angle counterclockwise direction with 30-degree angle? And sigma, so it's going to be sigma x prime, sigma y prime, and tau x prime y prime. If I define this, this axis is x prime axis, and this is going to be y prime axis, right? Okay, so this is very typical problem, and we can easily solve this problem using the Mohr circle. Again, to get the answer to this kind of a problem, we have to develop the Mohr circle. To develop the Mohr circle, we have to identify first these three stresses: sigma x, sigma y, and tau xy. What is sigma x? It's going to be 8 KSI in the negative direction, so it's going to be negative 8 KSI. Sigma y is going to be positive 12 KSI. Tau xy is going to be negative direction, so negative 6 KSI. So when we have identified these three stresses, then easily we can determine the location and the coordinate of these 3 points, C, A, and G. C is the center, sigma average, comma 0, A, sigma x, comma tau xy, G, sigma y, comma negative tau xy. So what is sigma average? We just take the average between these two. Negative 8 plus 12 is going to be 4, divided by 2 is going to be 2, right? So it's going to be 2 comma 0. Sigma x is negative 8, so negative 8 comma tau xy is going to be negative 6. This is sigma y, so positive 12 comma negative tau xy, which is negative, negative goes to positive, so it's going to be positive 6. So these three points is going to be the starting point our Mohr circle development. So here we have vertical axis, tau, and then horizontal axis, sigma, okay? And then we have to have all these points. So here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12. So it's up to 12 and -8. So it's going to be -8. No, 1, 2, 3, 4, 5, 6, 7, 8. And then in the vertical direction, it goes to positive and -6. So 1, 2, 3, 4, 5, 6. Of course, I'm not that accurate, but I'm trying to do my best. 3, 4, 5, 6. Okay, so let me just point these 3 points on this grid. So point C is going to be 2, 0. So positive 2 and 0. So this is going to be point C. And then point A, -8. So 1, 2, 3, 4, 5, 6, 7, 8. This is -8 and goes to -6. So we have to go up, right? 1, 2, 3, 4, 5, 6. So this is going to be point A. This was C. And then point G, 12. This was 12. This was -8, -6. 12 with 6 here. This is going to be my point G. And here was 2. Right? And these 3 points should be on the same line. So I'm going to draw a straight line from A, C. No. Do it again. So this is it's going to be one of the radius, right? The distance between A and C. And distance between C and G. This should be the same length R. And based on these, we can develop a circle. Half circle goes this way. And the other one goes this way. Okay, I know it's poor. Sorry about that. Okay, so again, on this line between AC, along this line AC and G, this is the current. This is current state of stress. Okay, and the question is asking, what if we change the angle 30° in the counterclockwise direction? So I said 30° angle in the real space, that is going to be twice. So we have to change the 60° in our Mohr circle. So first of all, we'd like to know how much angle here currently. So then we can define what is going to be the 60°. So when you calculate this angle, which is based on this triangle, so look at the triangle between point C, point A, and this is the projection of point A on the x-axis, which is -8, right? So the distance from A to this point is going to be -8 plus 2 is going to be 10. And the height is going to be -6. So in terms of the magnitude, it's going to be 6, right? So you can easily find out the angle here as tangent, arctangent, 6/10 will give us the angle directly, which is 30.96. So from this calculation, I'm going to use a phi. That's what the textbook used. So that this phi angle is going to be 30.96, and we have to change the angle based on this 30° in the real space. So we have to go way further down, right? We have to change the angle 60°. So I'm going to draw it something like this. So I'm going to use a different color. So we start from this original and current state of stress with 60 degree, okay? If you can find out the corresponding value of sigma and the corresponding value of tau, that will provide you the stresses on your stress plot after the angle change. Does that make sense? Because all the points on this Mohr circle will represent the state of stress. So when we change the angle 30 degree in the counterclockwise, so we move the 60 degree on the Mohr circle because this should be the double the amount of the whatever angle change. And then find out the coordinate, x coordinate and y coordinate. X coordinate will be the sigma and y coordinate will be tau. That's how we can solve the problem. Okay, so now we know this angle and this phi angle is 30.96. So we can say this remaining angle on the other side is going to be 60 minus 30.96, which is 29.04. So we can create another triangle here. And the angle is going to be 29.04 degree, right? So what we'd like to know is we'd like to know this base of this triangle and this height of the triangle. What we know is this, the radius. Radius is always equal to whatever radius here, right? So the radius, you can easily find out the radius from here. So r squared should be equal to 6 squared plus 10 squared. From there, the radius is equal to 11.66. So we do know that this side of the triangle is 11.66. And then we also know the angle here. So you can find out the base of the triangle and the height of the triangle. Height of the triangle is going to be exactly same as directly match with the tau value. The base of the triangle is not, because the center is not exactly at the origin. Center is at 2, 0. So whatever you have, the base of the triangle, you have to substitute 2 so that you can find out the coordinate of the sigma on this grid, right? So what we can do is, so look at the triangle. If you know the length here, we can set up the equation as this. Think about the sine of 29.04, this angle. How can you calculate the sine? The vertical, let me just call it x and y. Then sine of this angle should be y over this 11.66. So you can easily say this y is going to be 11.66 times sine of 29.04. Okay, and that y is going to be directly into tau xy. What about cosine equation? Cosine of 29.04 will be equal to x divided by 11.66. So you can find out this x and then substitute 2, then you will get sigma value. So from there, sigma x prime will be equal to negative 8.20 in KSI. Tau x prime y prime, which is this y value directly, is 5.66 in KSI. How can we find out sigma y prime? Either you just directly use the equation for sigma y prime, or when you calculate the value here, the value of your sigma on the other side, okay, that will give you the sigma y, because we now calculate the base of this triangle and we substituted 2, right? In this case, the base of triangle plus 2 will be sigma sigma y. So that is going to be they didn't calculate sigma y. Oh, they did. 12.2. So it's going to be 12.2. It's positive in KSI. So when you, these are the final answers. When you draw the stress block, it is going to be this way, and then since sigma x prime is negative sign, so we have to have a compressive stress with 8.20. Sigma y prime is positive, so it's okay. The tensile stress is going to be 12.2, and then our tau x prime y prime is positive, so the direction is correct, and the magnitude is going to be 5.66. Everything is in KSI. So that's how we can solve the problem. I'm going to save this one as well, and then I'm going to put it on the Blackboard. Okay, so that's the first video of week 15. See you later.